When a molten metal solidifies, the atoms arrange themselves into definite patterns called crystal structures. The two most common crystal structures in metals are body-centered cubic and face-centered cubic. These crystal structures grow uniformly in all directions within each developing crystal. As the metal cools, these crystals are confined by the adjacent developing crystals, forming grains. The line of intersection between grains is called a grain boundary. Because the grains form independently, their crystal structures develop tilted in various directions. All atoms in these crystalline structures are held in place by electromagnetic attraction to neighboring atoms. If a force or load is applied to a metal, these electromagnetic bonds stretch, allowing the atoms to move slightly. When the load is removed, the bonds pull the atoms back into position. If the applied force exceeds the metal's yield strength, those electromagnetic bonds will break, causing permanent stretching or deformation. This diagram is the iron-carbon phase diagram. Let's examine how temperature and carbon content combine to provide a variety of metallurgical structures. The left-hand side of this diagram is ferrite. Ferrite is iron containing an extremely minute amount of carbon. At room temperature, ferrite is magnetic, relatively soft, and has a body-centered cubic crystal structure. At room temperature, the solid solubility, or the amount of carbon that can be dissolved in ferrite, is practically zero. The amount of carbon dissolvable in ferrite increases to only a maximum of 0.025% at 1,333 degrees Fahrenheit. When heated to 1,670 degrees Fahrenheit, ferrite's body-centered cubic crystal structure rearranges itself into a face-centered cubic structure, known as austenite. This transformation to austenite is an important phase in the heat treatment of steels. Austenite's crystal structure allows it to absorb up to 0.80% of carbon at 1,333 degrees Fahrenheit, increasing to a maximum of 2.0% at 2,066 degrees Fahrenheit. The right-hand side of this iron-carbon phase diagram represents cementite, also known as iron carbide. Cementite contains 6.67% carbon. Though this phase diagram ranges from ferrite, with very low carbon content, to cementite, with 6.67% carbon, most steels contain less than 2.0% carbon. The carbon content is the major factor in determining the properties that can be developed in steel. The use of very low carbon contents or very high carbon contents provides many different steel compositions with very different properties. For this reason, steel is suited to a wide range of engineering applications. Let's take a closer look at some examples of how carbon affects the hardness of steels. If steel containing 0.030% carbon is heated to about 1,700 degrees Fahrenheit, the structure will consist entirely of austenite. If it is then cooled slowly at about 1,650 degrees Fahrenheit, the austenite begins to transform to ferrite. As cooling continues, more and more ferrite is formed, until at 1,333 degrees Fahrenheit, the remaining austenite transforms completely. Ferrite can retain only 0.025% carbon at this temperature. So to accommodate the carbon in excess of this amount, the remaining austenite transforms to a mixture of ferrite and cementite in alternating thin, plate-like layers. This structure is referred to as pearlite. At room temperature, The steel is mostly ferrite with patches of pearlite.